Okay, last time we've been talking about really sort of solution stoichiometry, really involving titrations. Solution stoichiometry really does work the same way as sort of regular stoichiometry. The main difference, as we sort of talked about last time, is really sort of how we get to moles. So instead of in a sort of traditional, if you will, stoichiometry problem where we're given grams and we use the molar mass to sort of convert things into moles, when we're dealing with solutions, obviously we usually don't have grams. So we usually have molarity or concentration. We usually have volume. So one of the main differences really is just how we get to those moles, and we use obviously our volume times our molarity, or our liters times our molarity, to really get to moles. And so that's sort of one of the really main differences there, is sort of how we get to the moles. Really, the rest of it is pretty much sort of the same. You do need obviously a balanced equation like a normal stoichiometry problem. You do need obviously convert to moles. Again, just the difference of how we got to get there. You do the mole to mole relationship. And really, the last part of it as well is sometimes that fourth step is also where see some differences. And a lot of times in sort of, again, traditional sort of stoichiometry problem, we're interested in maybe in how many grams we produced or something of that nature. Sort of solution stoichiometry problems, we're interested in a lot of times things like molarity. We may be interested in maybe how much volume we produced or something like that. So on the back end of a lot of times when we're doing these type of calculations, we also need to kind of use molarity or insert molarity in there as well. But pretty much everything else kind of in between is very similar, and pretty much the same sort of steps. In addition, you can definitely in a solution stoichiometry problem, have like a limiting reagent situation that's occurring. And again, the way you can recognize that, as we talked about a number of times up to this point, is if you do have enough information to get the moles of everybody there on the reactant side, however you could get that from the information given to you in the problem, then it is a limiting reagent problem. You again would approach it the same way as a normal limiting reagent problem, really with the main difference being, once again, how you get to moles, which is in the volume and the molarity. We specifically sort of talked about solution stoichiometry involving titrations. Titrations, obviously, like we talked about yesterday, and sort of the experiment we're doing this week, is basically when we sort of add a solution of known concentration to like a solution of unknown concentration. And we can basically use stoichiometry to figure out some information about the unknown solution. So, for example, in part one of like our experiment, we made a solution that is a known solution of an acid, while we also made a solution that's an unknown solution, really, in terms of its molarity of a base. So by performing a titration, we're able to basically use stoichiometry to figure out things like what the concentration is of that unknown sodium hydroxide, for example, in the case of the experiment. So we basically add slowly, from a burette, the solution. And when we do a titration, right, there's a couple of really important things as you do it. First off, obviously, you should always take an initial volume reading and final volume reading. You also should use an indicator, and we typically do titrate to what's referred to as the equivalence point. And specifically in an acid base titration, the equivalence point basically represents the point where exactly equal amounts of moles of acid and base have been added to the solution. In essence, the equivalence point basically means when the reaction is sort of complete or done. And obviously, when we use an indicator in the titration, it visually gives us a sort of sense of when that is by changing color. And as we talked a little bit about indicators, indicators do work over a pH range, as we talked about. They have different colors in acidic solution versus basic solution. Um, and usually you want to pick one where you can't see a distinct color change occur, um, near your equivalence point, so that uh, that you should physically stop. Any questions on the stuff that we sort of talked about last time? Okay, so just kind of continuing on, we're going to talk about some other types of concentration units. although molarity really is sort of the most commonly used concentration unit for solutions. And again, molarity being our moles per liter. There definitely are other units that are associated or that we do come across when we're dealing with solutions. One is what is referred to as the mass percent or percent by mass. And this is sometimes abbreviated as percent m/m, which basically means mass to mass percent. And it is the mass of the solute, which is the smaller part of the solution, divided by the mass of the solution times 100. Now, the bottom part is really important, especially in these type of problems. It is the mass of the solution, and a reminder that a solution is basically made up of two things, the solute and the solvent. And you want to make sure that you actually do get both of those things on the bottom there. So it's very common in these type of problems that they will give you the information separately. So they'll kind of tell you the mass of the solute by itself. They'll tell you the mass of the solvent by itself. And it's very common sort of error that people make, that they basically just divide by the mass of the solvent alone. So unlike a lot of them, it is kind of a lot of times given to you separately. So you do want to make sure that you do get actually the entire solution there on the bottom and not just the mass of the solvent. When we talk about something being a certain percentage, we sometimes can convert it into a more usable sort of unit, if you will. So, for example, if we had 4.5% by mass sodium chloride solution, what that basically means is, since we have a percentage, we can't convert it into a usable sort of conversion factor. We basically could say in that case that there would be 4.5 grams of sodium chloride and 100 grams of solution, which is basically 4.5%. You could also flip it around if you're doing a little dimensional analysis and need kind of the conversion factor used the other way, and you can flip it sort of around this way as well. So sometimes it's again useful to kind of convert these percentages into sort of useful conversion factors that you can use for calculations there. And again, that's basically what it means. Same idea as what we talked about when we kind of see 4.5 molar sodium chloride. That basically means that there's 4.5 moles of sodium chloride per liter. Or again, you could flip it around as we talked about and kind of do it as dimensional analysis, and got a conversion factor as well. So these again are kind of two common units of concentration. There's actually some other sort of percent units that we sometimes come across, and they sort of work the same way. So we have percent mass to mass. We also have, in addition to that, percent volume to volume. And percent volume to volume basically means the volume of solute divided by the volume of solution times 100%. So that's another sort of percent concentration. Another one is percent mass to volume, which would be the mass of solute over the volume of solution times 100%. So these are three sort of percent concentrations, if you will, that are also very much used in solutions. And in terms of units and sort of how these guys work, they work basically the same way as the other guys there. Again, if you need to convert it into sort of a usable conversion factor, if you said you had 4.5% volume to volume, that basically means that you would have 4.5 milliliters of sodium chloride, of sodium chloride and 100 milliliters of solution. Or again, you can flip it around the other way, 100 milliliters of solution, you have 4.5 milliliters of sodium chloride. And same thing if you had kind of 4.5% mass to volume of sodium chloride, that would mean you had 4.5 grams of sodium chloride in 100 milliliters of solution, or in 100 milliliters of solution, you had 4.5 grams of sodium chloride. So again, you can use these definitely as sort of conversion factors for each of these. And again, sometimes it's easier to sort of do that. You definitely can't just plug and chug sort of into these formulas as well and solve for whatever is missing. You know, that works the same way. It's really the same math. This is sort of a preference as to how you want to do it. A reminder as well, as we've talked about before, the solute is the smaller part of the solution, solvent is the larger part. The good news on sort of these guys is you don't usually have to worry too much about the bottom part here, because usually in these problems they just straight out give you the volume of the solution. It's really just this one here that you do need to make sure you get both the solute and the solvent together. Any questions on that there? So let's take a look at one here and see what we come up with. All right, so why don't you take a second here and calculate the percent mass to mass here of this guy. So what is the percent mass to mass of a solution prepared by 2.5 grams of calcium with 50 grams of water? Calculate the percent mass to mass. Okay, let's take a look here. So we're making a solution by taking 2.5 grams of calcium chloride with 50 grams of water. So a couple of things. First off, the calcium chloride here, which is 2.5 grams, that would be our solute. It is the smaller part of the solution. 50 grams of water would actually be our solvent. So we do have the mass of the solute given to us, which is 2.5 grams. We have the mass of the solvent given to us, which is our 50 grams. And remember that alone, these are not the solution, but when you add these together, that would give you the mass of the solution, which again is a very common mistake that people sometimes make here when they're doing our percent mass to mass, which obviously is the formula that we saw before. And that is the mass of the solute divided by the mass of the solution times 100%. So again, you don't want to just use the solvent. You want to make sure in this case that you do add it together and you get the entire solution's mass. At this point, we got everything we need to basically plug it into there. So the percent mass to mass here would be our solute, which is our smaller part up on top. Our bottom part, again, the entire solution, not just the solvent, times it by 100%. Looking like perhaps we get 4.76. And the way we leave it is in terms of this percentages. So usually you write percent and a little m/m next to it to indicate that it's mass to mass percent. And I could also put calcium chloride there. If you like. Question on that calculation there. So again, like I mentioned before, you know, you want to really be careful, especially in these type of problems. It's very common, very much like this problem, that you're sort of given the solute and the solvent information separate from each other. You want to make sure that you do add them together. Any questions on any of that calculation there? All right, so why don't you try another one here? What is, we got a concentrated hydrochloric acid solution. Contains 37.2% by mass hydrochloric acid. What is the mass of the hydrochloric acid in 35.5 grams of the solution? Take a couple minutes, see what you come up with. Yeah, let's take a look at this one. So basically they told us that we have a percent mass to mass of 37.2% HCl. And they basically told us that the mass of the solution is 35.5 grams. And we're looking for basically the mass of the HCl. So we're really looking for the mass of the solute, right? And HCl here is the solute, as we talked about, I think, a number of times. When we talk about sort of the concentration of a solution, really the name of the solution, right, is the solute. So we do know that's what we're looking for. So clearly we can kind of plug and chug into the percent mass to mass sort of formula that we just saw. I'm also going to use this and sort of solve it a little bit of a different way, more of a dimensional analysis approach and sort of conversion factor. So as we talked about before, you can really kind of turn this into some usable conversion factors. Basically what that means is we would have 37.2 grams of HCl in 100 grams of solution, or in 100 grams of solution, we would have 37.2 grams of HCl. So I'm going to kind of do dimensional analysis approach since we already know the grams of the solution. We're going to go 35.5 grams of solution. We need the solution to cancel out, which means we want to use the conversion factor there on the left, which would be 100 grams of solution is 37.2 grams of HCl. Grams of solution cancel each other out, and we do end up with 13.2 grams of HCl is dissolved in there. And that would be our answer there. Any questions on that? Now, that's again a more sort of dimensional analysis approach. Clearly, you could just go with the formula that we saw for it. And again, you do have this obviously given to you. That would be our 37.2%. The mass of the solute, which is what we're looking for. The mass of the solution was 35.5 grams times 100%. And math-wise, when you rearrange this, you're going to multiply the 35.5 to the other side and divide by the 100, which is basically the same math that you did here. So again, it was sort of a preference, however you want to do it. Again, this sort of lines everything up so you can kind of see what's canceling. Maybe less of a chance of some rearranging problems, but definitely it's basically the same exact thing as plugging it in, solving for it. Any questions on how to do percent mass to mass, percent mass to volume to volume? Again, those other guys basically work the exact same way, except obviously you're seeing volume and volume or mass and volume. All right, so now we've seen a few different types of sort of concentrations. We've seen molarity. We've seen percent mass to mass to volume to volume, sort of our percentage type concentrations. There is another sort of concentration unit that does pop up, and we personally will see it. And it does pop up as solutions. We personally will see it towards the end of the class and like a couple of those last chapters. And that is actually what is referred to as molality, if I get it. Now, molality, not to be confused with molarity, they are different. So for purpose sake, big M, dramatically drawn there, is molarity, which is what we talked about previously, which is our moles per liter. Little m, which is not mass or anything like that, is in this case is molality. So it's kind of sound alike. They kind of have similar sort of symbols, if you will, but one is capital, obviously, one is lowercase m. And it actually is a little bit different. So the molality of something is the moles of solute divided by the kilograms of solvent. So the moles of solute divided by kilograms of solvent. And kind of in our example we've been doing, we can kind of also say if we have 4.5 molal, which is sort of how it's abbreviated and referred to, kind of like molarity is molar, this is molal, say sodium chloride, that would again mean that we have 4.50 moles of sodium chloride in a kilogram of solvent. So again, that's a common sort of unit. It's used, as we will see in a couple later chapter there, in what's referred to as colligative properties. It uses this sort of concentration unit a lot. So it will definitely pop back up. So don't get those guys confused. Again, molarity, big M, moles per liter, molality, little m, moles per kilogram of solvent. And in case you're curious, the sort of thing that ties these two together is the density. So the density is sort of what you need to basically go from one to the other. So you need like the density of the solvent or the solution there to allow you to kind of convert from one to the other. And that's sort of the thing that bridges sort of both of those things. So why don't you try one here and see what you come up with. Calculate the molality of a solution that's prepared by dissolving 61.7 grams of C3H7OH in 175 grams of water. Some numbers you might need from the periodic table. Carbon 12.01, hydrogen 1.008, and our good friend oxygen at 16. All right, take a minute or two here and see what you come up. Okay, so we are looking for the molality here. And again, the molality, as we just saw, is the moles of solute divided by the kilograms of solvent. So again, just some recognition of what we're dealing with. Remember, the smaller part of the solution is the solute, and typically that's the thing you're dissolving. So since we're dissolving this guy here, that guy probably should be our solute. Water is the larger part of the solution in this particular case, and that would be the solvent. So in terms of the solute, we do need to convert our grams into moles. So we need to get our molar mass of our C3H7OH. And that is going to be 3 times our 12.01 for our carbon, plus 8 times our 1.008 for our hydrogens that we have there. And we got 1 oxygen that is there. That gives us a grand total of, I think, 60.09 grams per mole. So the first thing that we'll do is we'll take our grams of that solute there. We're going to divide it by the molar mass, basically putting the grams on the bottom so that they cancel out. Grams will cancel, and looks like we end up with there, call it 1 point, we'll call it 1.03, 1.03 moles. We then have the top part here, bottom part, we need kilograms. They actually gave us 175 milliliters of water, and they gave us the density. So as we just saw a second ago, density is mass divided by volume. They gave us the density and they gave us the volume. That's going to allow us to solve for M, which is mass. Mass would be volume times the density. So in this particular case, we have 175 milliliters of water, which is our solvent. The density in this case is 1 gram per milliliter, so not too bad here. That is going to give us 175 grams of water. Remember, though, that we don't need grams, but we do need kilograms. So we do need to do one little conversion on that guy as well. There's 1,000 grams in a kilogram here. Grams will cancel, and that will yield us 175 kilograms, 0.175 kilograms. Now we have basically both things that we need. We can stick it into our equation here. The molality would be our moles, which is 1.03 moles, divided by 0.175 kilograms for our solvent. And we do end up with here, we'll call it 5.89. Now, in terms of units, they really don't cancel out, kind of like molarity. So 5.89, technically you have moles per kilogram. And that really is kind of like molarity, that you could, if you wanted to, write 5.89 little m. And obviously this would be the C3H7OH. So you could give the answer either way. Again, the units do not really cancel out, but just like molarity is moles per liter, moles per kilogram is molality or little m. So you could basically display it either way. Any questions on any of those numbers or where they came from? Okay. All right, and sort of finish up this little sort of chapter-ish that we've been talking about, concentrations and stuff like that. Another sort of, guess you could call it a concentration, is something, again, we will also see here in the next chapter when we talk about gases. We'll also see it also later on as well when we talk about colligative properties. And that's the mole fraction. And the mole fraction is really like a percentage without the multiplying by 100 part. It's basically the moles you're interested in divided by the total moles that are present. The mole fraction is basically represented by X, or big X there. And for example, if we had, say, a solution or something like that that had, moles of A floating around, moles of B floating around, two different things, we would take the mole fraction, say, of A would be the moles of A over the total moles. Again, we wouldn't multiply by 100. And obviously the total moles in my example here would be the moles of A plus the moles of B. You could do the same thing for B in this case. You would just take the moles of B that are present divided by the total moles again. No multiplying by 100 here, so it's not a percentage, which means the maximum that you get to 100% equals 1. So that's why it says it equals 1, because we're not multiplying by 100. So, when you add up everybody there in terms of the moles, all the mole fractions should equal 1, which is equivalent basically to 100% of what's present. Any questions on mole fraction there? All right, so why don't we try one here and see what you come up with. We want to calculate the mole fraction of methyl alcohol, which is the CH3OH in the solution is composed of 0.328 moles of methyl alcohol and 0.929 moles of ethyl alcohol. So take a second here and see what you come up with. Okay, so again, we're looking for the mole fraction. So basically in this case, one of the things that we do need is the total moles. And the total moles in this case is basically just adding both together. So we got 0.328 for our methyl alcohol, and we got 0.929 for our ethanol. And that gives us a grand total, if we add those guys together, 0.328 plus 0.929, looks like 1257 moles. And in this case, we are interested in the mole fraction of methanol, and that is our CH3OH. So that would be the moles of methanol divided by the total moles. And the moles of methanol in this case, again, 0.328 divided by our 1.257. Again, no multiplying by 100 here, not a percentage. Looks like we end up with 0.261, we'll call it. We could also do the exact same thing for the other guy there. It wasn't asked to do so, but if we wanted to get the ethanol, we would just simply take the moles of the ethanol divided by the total moles, and that would get us 0.739 as the mole fraction. Basically what it is 26% methanol, 74% basically ethanol. Again, not technically a percentage. The other thing you could have done is, because these are only two things present in the solution, again, 100% would have been 1. So you could have at that point took 1 minus 0.261 and get the mole fraction of the other guy. Again, 1 representing basically 100%. Any questions on mole fraction? Again, we will see it actually in the next chapter, gases, and we will see it a little bit later on in the semester here as well. Any questions on any of that stuff there, different concentration units? Okay. All right, so that actually should wrap this sort of chapters, parts of different chapters. We're now going to go to the next chapter, which is gases is what we're going to cover next, which should be chapter 8. So get that going here. Okay. So obviously in chapter 8, we're going to talk about gases. And obviously we are talking about at this point the state of matter, where pretty much everybody is broken apart from each other. They're flying around. As they're flying around, there's numbers of collisions that are occurring as these guys are basically moving. The collisions that they occur basically is what we associate with pressure when we think about gases, and sort of the pressure that they exert. So we're going to talk about some gas laws here. You do need to know the gas laws. You will probably have maybe seen some before. We'll see some gas laws maybe you haven't seen before, but you do need to kind of know those guys as we go through them. First off, a couple of things. Let's talk about, what substances really can exist as gases under normal conditions. When we talk about normal conditions, it's sort of like room temperature, I would say room sort of temperature conditions, if you will, everyday conditions. And that's usually basically 1 atmosphere. ATM is a unit of pressure, and 25 degrees Celsius. So that's sort of like your standard sort of pressure and temperature of normal conditions. That's anytime you kind of look up values in a table, like in your book or the back of the book, those are usually sort of the conditions at which sort of those values are found. Temperature is assumed to be 25 degrees and 1 atmosphere. Now, under these sort of normal conditions, ionic compounds really do not exist as gases. And that's because they're held together by really strong electrostatic attraction or electrostatic forces. And those are really strong intramolecular forces. Molecules are forces within an actual molecule. And what typically happens when we have an ionic compound is you could heat it, and it typically will not go into the gas phase. It will really start to melt first before it'll actually kind of go into the gas phase. An example of that, just think about sort of sodium chloride, salt, right? When we heat up sodium chloride, if you heat up salt water or something like that, what typically happens is as you heat up something like salt water, the water evaporates, and what you're left with is a residue of salt, which doesn't really go away and evaporate and go into the gas phase. It will just start looking like it's starting to melt and stuff like that. And that's very different than what we see with sort of molecular compounds that actually share electrons and stuff like that. We see that when we're dealing with those guys, there are some molecular compounds that are just gases right out of the gate. So things like carbon monoxide, carbon dioxide, that's hydrogen chloride gas, ammonia, and methane. These are all gases. But a lot of molecular compounds really are liquids or solids at room temperature. But the major difference sort of between a molecular compound, which again is more covalent bonding and sharing of electrons, versus an ionic compound, which is using electrostatic attraction, is you can much easier convert a molecular compound usually into a gas than you can obviously an ionic compound. And that's because the difference between sort of an ionic compound and a molecular compound is sort of how they are put together. And we'll talk a little bit more about this in a later chapter, but there's really 2 types of forces. There's one that's referred to as an intramolecular force. And intra means within the molecule. So we just take water, for example, just one water molecule by itself. The intramolecular force is really the covalent bonds between the oxygen and the hydrogen, the sharing of electrons that are happening there. When we talk about an intermolecular force, that is the force between basically 2 different molecules. So that's the force that holds together when you take, say, one water molecule, which is polar, right? And another water molecule, which is also polar, and is that force that basically holds those two together, is the intermolecular force. And when we talk about the strength of these differences, intramolecular force versus intermolecular force, the intermolecular force is much weaker than an intramolecular force. Intramolecular force, for example, in an ionic compound is that electrostatic attraction between the positive cation and the negative anion. Intramolecular force between one single water molecule is the individual covalent bonds. And we know that for sure because when we go and heat something like water, like on the stove, if you're going to make pasta or something like that, when you start to heat that thing, the very first bond that breaks is actually this bond, the bond between one water molecule with another. And that allows these guys then to become basically steam, right? Gas molecules as they kind of come out. If it was opposite and the intramolecular force was weaker, when you would go heat something like water, each water molecule would fall apart and you would get hydrogen gas and oxygen gas, which is not so good because, you know, that would not be a great idea, especially if you're heating it. So we know that doesn't happen. So because basically molecular compounds are held together by these intermolecular forces, it is much easier to break those guys and convert them into the gas phase than something that's ionic, which is really held together by a very strong intramolecular force. Any questions on that there? So what are some substances that are found as sort of gases under normal conditions where things like our hydrogen, nitrogen, oxygen, fluorine, and chlorine. So those are all of our diatomic molecules that are elements that we talked about. These guys in their normal sort of situation are obviously gases. Ozone, which is O3, is a gas. And then obviously our group 8, which is our noble gases. Those are monoatomic, which means they come as one. So that's our helium, our neon, our argon, our krypton, and our xenon. And that's what we see here again, our sort of guys in blue are naturally sort of gases under sort of normal conditions. So what are some of the properties that we associate sort of with gases? Gases assume the volume and shape of their containers. So as gases are flying around, they're obviously filling up that container uniformly. Gases are the most compressible state of matter. Obviously, if you try to compress, say, a liquid, it doesn't work so well. It makes a kind of a mess. Gases will mix evenly and completely when they're in the same container. So if you have multiple gases kind of flying around in a single container, they're going to mix just by the process of flying around, basically, right? So, I mean, if they're in a container and they're flying around in the same container, they have no choice but to basically be mixing with each other, and they're constantly basically mixing, which means they're very soluble in one another as well. Gases, on the other hand, do have a much lower density than liquids and solids, and typical units. We actually do see some different units involved when we're dealing with sort of gases versus, say, solids or liquids. So here. Yeah, so the question is bromine and iodine diatomic as well? They are, but they're not gases under kind of normal conditions. Bromine is kind of what we see there on the left there. I believe that's bromine there, if I'm looking. It's sort of like a liquid with like a gas sort of vapor over it, and iodine is more of a sort of a liquid and stuff like that, but they are diatomic. All those guys in group 7 for the most part, F2, Cl2, Br2, and I2, when they are by themselves, they are diatomic. But in terms of sort of normal conditions, kind of only really fluorine and chlorine are kind of considered gases under normal conditions. So when we talk about densities, of solids or liquids, we usually have units of grams per milliliter or grams per cubic centimeter. When we talk about densities of gases, we typically talk about in terms of grams per liter, and we will see that a little bit later on in this chapter. We're going to talk about how to basically calculate the density of a gas. So it's important to talk about some important units associated with gases, and there's several different types of units, if you will. But basically, the pressure is the force divided by the area, and mass times acceleration. A Pascal is a unit of pressure, and that equals 1 Newton meter. Another sort of common unit, in addition to pascals, is actually what is referred to sometimes as a kilopascal. And basically, it's basically like the kilo prefix there. This is 3 common units that are used a lot in chemistry, and that is an atmosphere, which is an ATM, is equal to 760 millimeters of mercury and 760 torr. And that is because when we measure atmospheric pressure, we usually sometimes will use a device that is known as a barometer. And this is sort of a classic barometer that we see here to the right. A classic barometer has basically mercury and a glass tube that's filled with mercury as well. And as atmospheric pressure basically exerts on the mercury on the pool, it allows the mercury obviously to kind of go up or down depending on how much pressure there is, and it affects obviously the mercury that is there. Now, one of the units that we commonly use for pressure is mmHg, and that does stand for millimeters of mercury. And that is because a barometer is usually made up of mercury. Not anymore. They've taken it out because mercury is not so great for everybody. But classic barometers are made up of mercury. And basically on the tube or near the tube would be like a ruler where you could take a reading in either millimeters or inches or centimeters, depending on sort of the measurement that you have. So sort of the common unit to give sort of a nice biggish number and whole number is millimeters. And that's what mmHg really stands for, millimeters of mercury, sort of the ruler that you would read of how high the mercury is in the column. Mercury is an unusual thing when we read it. We do read it based on the meniscus, but mercury actually has a reverse or an inverse sort of meniscus. It actually curves upwards. I kind of wrote over the other one, but you can kind of see it here. It kind of curves upwards, and you actually read it towards the top of the curve there would be where you would read the mercury when you're taking a reading. And the other unit of pressure that's commonly used is a torr. And a torr basically is named after the guy who kind of invented the barometer, Torricelli. And 1 millimeters of mercury is the same thing as a torr. So there are a 1-to-1 relationship between those two things. So if you have a millimeter of mercury, it's the same thing as having a torr. And obviously an ATM, no money out of that one, which is an atmosphere, is another unit. You can see that 760 is sort of our number, and 760 is the number that we use to do the conversions between the different units. So if you have atmospheres and you want millimeters of mercury or torr, you're going to multiply by the 760. And that will give you a millimeter of mercury, which is the same thing as a torr. Or if you have a millimeter of mercury or a torr and you want atmospheres, you're going to divide by the 760. And that will give you atmospheres. So that 760 number is sort of a really important sort of number. It allows us to kind of convert between the 3 most common units. Again, some other units, an atmosphere is equal to 101,325 pascals, or as I said before, a kilopascal is a common unit. So, basically 1 atmosphere is equal to 101.325 kilopascals. Other units of pressure that you sometimes come across is a bar. A bar is basically like an atmosphere. It's like 1.01 sort of atmospheres to a bar, so they're very almost like one-to-one relationship. So a bar is another common unit of pressure. Obviously, PSI, pounds per square inch, is another common one that's used. And again, when you fill up, obviously, like tires and stuff like that, is given in pounds per square inch. The pressure is affected by sort of your distance from sort of sea level, for example. So as we can see here, the pressure decreases as you get sort of higher above sea level. Differences in pressure and stuff like that, and elevation has an effect on things like boiling points and stuff like that. You could get water to boil at some different temperatures depending on sort of your atmosphere and the pressure that's sort of associated with it. So let's talk a little bit about some some equipment that's used to sort of study gases and pressures and stuff like that. And these are manometers, and they're used basically to study sort of, pressure of gases and allow you to sort of figure out the pressure of gases. We have sort of two types of systems. This is a closed system. You can see it's capped off there. And in a closed system, the pressure of the gas that would be in this sort of apparatus, basically what's happening here is the gas has got nowhere to go. So it kind of comes through, it's got really nowhere to escape. And obviously it pushes the mercury, right? And the mercury basically starts to move within the tube. The pressure of the gas in sort of this closed situation is really just the height of the mercury in the column. In this system here, this is more of an open system. And that means it is open to atmospheric pressure. So same idea sort of happening. Gas kind of comes through, it then eventually starts pushing the mercury through the column. The difference is, in addition to that, you also do have some atmospheric pressure kind of pushing down on it as well. And that means that the pressure of the gas in this type of system is equal to the height of the column there and the pressure from the atmosphere as well. Sort of a correction value that you have to do in that sort of open situation based on atmospheric pressure. So we're now going to talk about some different gas laws. And when we talk about some gas laws, there's really sort of three variables that we oftentimes will deal with. And the three variables that we see sort of in gases is P, which is pressure, V, which is volume, and T, which is temperature. And in a lot of situations, we keep one of these guys constant and we sort of vary the other. In other situations, we may actually vary everybody there. But these are the three sort of main sort of guys that we look at. So sort of the first relationship that we're going to look at is the relationship between pressure and volume while we keep constant temperature. This relationship is basically what is known as sort of Boyle's law and Boyle's law relationship. And what we see here, if we look at sort of the apparatus, is at 100 milliliters in terms of our volume, we have this sort of pressure that's only about here. When we go to 50 milliliters, we see that the mercury starts to rise. So we have the much bigger sort of pressure that's occurring. And obviously, when we get to a very smaller volume of 33, we see an even bigger sort of rise in the pressure. So the relationship that we see here is sort of an inverse relationship. As the pressure goes up, the volume goes down. And as the pressure goes down, the volume goes up. And that's really is sort of Boyle's law relationship. And if you just think about it logically, if you drop the volume where the gas is moving around to very small volume, that means that really the gas molecules, which are constantly flying around, does not have a lot of space to fly around in. That means that there's going to be a much bigger increase in collisions that are going to occur. So if everybody's sort of in a very small closet or something like that, and you try to move around, there's a very good chance you're going to start colliding with people in that very small closet, rather than if you put the same amount of people in a much larger room there's a lot more room for people to walk around each other without maybe colliding into each other. And that's sort of the same idea with the gas. If we're able to kind of put that gas in a much larger volume, it gives them a little bit more room to fly around in. It's going to take longer for collisions to occur, and that's going to result in sort of a lower pressure than, again, if we're in a very small sort of area where there's going to be constant collisions basically occurring. As I mentioned before, that is what is referred to as Boyle's law, that inverse relationship. As one goes up, the other goes down. And sort of the mathematical version of Boyle's law, which is on the bottom here, and I'll write up on top, and that is P1 V1 is equal to P2 times V2. This is sort of a before and after situation, and this is at constant temperature. And again, pressure goes up, volume goes down, and pressure goes down, volume goes up. Now, an interesting thing about a lot of these gas laws and why you could kind of do a before and after sort of situation is if you take any pressure and volume sort of relationship when you're sort of studying Boyle's law and you multiply it, those values together, you always come up with the same constant number as long as the temperature remains constant and stuff like that. And that allows us to set them both equal to each other. And again, we get our P1 V1 equals P2 V2. Pressure in this case on both sides could be any unit you want as long as they are the same units. And volume as well can be any unit you want as long as they are the same on both sides. And graphically, that is what we see here. We see at very low volumes, much higher pressures. As the volume starts to increase, we see a much lower pressure basically occurring if we go back. And again, that linear relationship between the pressure and the inverse of the volume there gives us that linear relationship of what we see. All right, so I want to take a second here and calculate what we got going on here. A sample chlorine gas occupies 946 milliliters at a pressure of 726. What is the pressure when we take the volume to 154? This, and although obviously we've only talked about one gas law at this point, a really good approach when you're dealing with sort of gas laws is to really just kind of pull out the information from the problem. And oftentimes will point you in the right direction in terms of what gas law you should use. So 946 milliliters is obviously a volume. We obviously have a pressure that's 726 millimeters of mercury. We want to know what is the pressure and if the volume is 154 milliliters. So again, you could pretty much see Boyle's law there, which is our P1 V1 is equal to P2 V2. Doesn't matter which ones you put as ones or twos. It really doesn't, as long as you keep the sort of numbers together that go together. So we'll just kind of call these guys ones. We'll call these guys twos. And at this case, we're obviously solving for P2. So P2 means we're going to divide the V2 to the other side. That gives us P1 V1 divided by V2. Putting our numbers in there gives us our P1, which is 726 millimeters of mercury. Our V1, which is 946 milliliters, divided by our 154 milliliters. Milliliters will cancel, same unit, so that's all good. And if we do that, we will end up with 726 times a 946 and divided by 154. Gives us something like 4459.7 units here would be millimeters of mercury. And we probably want to clean it up perhaps to about 3 significant figures, since everybody else is 3 sigs big. So like 4460 millimeters of mercury here. Any questions on that calculation there? The question is, why do you not convert milliliters to liters? The answer is you don't have to in this case. You could if you wanted to. You could convert this guy to liters and this one to liters if you like. It's not necessary in this case as long as they are both in the same unit. Whatever unit of volume it is, as long as they're the same, it will basically cancel out because you're basically dividing by that unit. So you definitely could convert it to liters if you want to. You should end up with the same answer at the end, but it's not necessary in this particular case because of that. And that pretty much goes for most gas laws, as long as really kind of the units on both sides are the same. You usually don't have to do any type of conversion. You only have to do a conversion where, for example, if you have, say, one that was in liters and one that was in milliliters, then you definitely have to do a conversion. But you could do it to whichever unit you want in that particular case. They just need to be the same. In addition, we can also look at sort of our relationship here, and just to make sure, it sort of makes sense. What we see here in terms of volume, right, is the volume is actually decreasing. So the volume is going down, which means that we would predict that the pressure should go up. And it went from 726 to obviously 4,400. So it definitely went up. So this does fit with our Boyle's law sort of understanding. We lowered the volume, we should expect an increase in pressure. So, it's a good way to sort of understand what's going on, and a good way to check to make sure you didn't maybe superimpose some numbers or something like that. All right, let's try another one here. So take a second here, see what you come up with. We are looking for the final volume here in this case. Okay, let's take a look at this one here. So taking the same sort of approach, if we kind of pull out the information from the problem, we got 0.55 liters, which is definitely a volume. It's at sea level, which is 1 atmosphere. 1 atmosphere, remember, is a unit of pressure. It rises to 6.5 kilometers, useless information, where the pressure will be 0.4 atmospheres. And we're looking for our final volume. So again, you should hopefully be able to kind of see Boyle's law, which is P1 V1 equals P2 V2. And again, we could do the numbering like we talked about, just basically the first ones in the problem are kind of labeled 1, second ones are labeled 2. So we'll call these guys going this way. In this case, we're solving for V2. And a reminder, just an easy way to rearrange some of these gas laws is probably not too hard. We're obviously going to take our P2 to the other side. When we do go across an equal sign, although it's not written as a fraction, you kind of think of it like that. So just to help you quickly understand it, when you go across an equal sign in a situation like this, basically people end up in the opposite location, which means if I'm taking the P2 to the other side, it's going to end up on the bottom, right? And that gives us that P1, V1, P2 is equal to V2. So with gas law, sometimes people have trouble rearranging things. So you can think of the equal sign and, kind of think of both sides like a fraction. So if what you need to bring to the other side is on top, it goes to the bottom. If what you need to bring from the other side is on the bottom, it goes to the top, and vice versa, obviously, as you cross the equal sign. So that's a very quick way to rearrange sort of the formulas and sort of help yourself figure it out. In this case, we're good to go. Again, in units, we just want to check these two, and we are in the same units, which are atmospheres. And that means that V2 would be our P1, which is 1 atmosphere, times our V1, which is 0.55 liters, and divided by our 0.4 atmospheres. In this case, the atmospheres will cancel. Now, the importance of units as sort of to the earlier question, in this particular case, the volume was given to us in liters, which means when we do solve for it, we will be in liters as well. And that gets us 1 times 0.55 divided by 0.4 gets us, we'll call it, excuse me, 1.4 liters here. And again, the units here would be liters because that's what unit is left over. We can look at our sort of situation and see, does it make sense? In this case, our pressure went down, which means our volume should go up, and it went from 0.55 to 1.4. So again, that does make sense in terms of our relationship. Question on Boyle's law here. All right, then let's talk about another relationship. And now we're going to look at, in this case, the relationship between a couple of different relationships, but we're going to look at the relationship here first off between volume and temperature, holding constant pressure, and that is different than our another relationship. We'll first look at this one. That is what is referred to basically as Charles' law. Charles' law is V1 over T1 is equal to V2 over T2. That is volume on both sides. That is temperature on both sides. Another relationship that we see is the relationship between pressure and temperature, holding constant volume in that case. And that is what is known as Guy-Lussac's law. And that is P1 T1 is equal to P2 T2. This again is at constant volume in this particular case. So let's take a look at sort of what we expect to sort of happen here under these situations. Well, let's talk about first off here in this situation. In this situation, if we have a constant volume for the container, which means nobody's moving, that is what the container is, the size of it. If we were to increase the temperature in that situation, we would expect the gas molecules to start to move a lot faster, which means as they're starting to move a lot faster, there's going to be an increase in the number of collisions. And an increase in the number of collisions will result in an increase in pressure. And we would expect sort of that relationship that as the temperatures increased, everybody's moving faster, more collisions, pressure also increases. Vice versa as well, again, in this sort of fixed volume, if we lower the temperature, everybody's moving around a lot slower, which means it's going to take a little bit longer for them to come in contact with each other and the walls of the container, and we're going to expect the pressure to start to decrease. So Guy-Lussac's situation, as we decrease the temperature, the pressure will also drop as well. And that's because we have sort of this fixed volume, if you will, not moving. It's rigid, is sometimes referred to. Now, what happens in sort of Charles' law situation is we do not have a fixed volume. We have a fixed pressure. And that means that in a situation, if we have our volume here and we increase the temperature, the only way to maintain the pressure and keep the pressure constant would be for this volume then to increase as well. And what we will see is the volume would increase. And what that's going to do is give everybody a little bit more space to fly around. It's going to keep the collisions relatively constant, and it's going to keep the pressure from going crazy as it did in this situation on the right-hand side. And vice versa, what's going to happen is if we decide to lower the temperature, everybody's going to be flying around slower, which means there's going to be less collisions. So what happens with the volume is, in Charles' law situation, is it corrects itself. The volume goes down in this situation. And what that does is it basically gives everybody less room to fly around, increases the number of collisions, and keeps the pressure constant. So in Charles' law situation, what we see is as the volume goes up, so does the temperature. And that's what allows it to maintain constant pressure by changing the volume or increasing the volume. As the volume goes down, the temperature goes down as well. Again, what allows it to keep that constant pressure is we have a lot less collisions at a less temperature. We're going to drop it down, cause a lot more collisions, and keep our pressure relatively constant to each other. Any questions on the differences there? And that is sort of what we see here when we look at our pressure here. Pressure is constant in both cases. At a lower temperature, we have a much smaller volume. At a higher temperature, in order to keep that pressure constant, we need a much bigger volume that's happening in this particular situation. And those are basically two gas laws that are similar in that sense, but a little bit different because, again, one is dealing with sort of the volume shifting to maintain the pressure. In the case of Guy Lussig's on the right there, because there is constant volume, there is no the shifting of the volume. So because of the temperature goes up, there's no place for those gas molecules to go. Pressure basically increases as well. An interesting sort of relationship that we see when we plot sort of Charles' law relationship on a graph is that we do see that no matter what gas you take, so these are all different gases, if you plot basically volume versus temperature in degrees Celsius, and you sort of extend their straight line back to the temperature spot, every single gas hits the exact same place. Every single gas hits a temperature of minus 273.15 degrees Celsius. Now, that number may look familiar to you because if you remember, to convert a temperature into Kelvin, it is the temperature in Celsius plus 273, technically 273.15. That means that if we were to convert that Celsius into Kelvin, 273.15 is 0 Kelvin. That is what is sometimes referred to as absolute zero, and used to be the absolute temperature scale, a later name for the for Kelvin and the Kelvin temperature scale. There is a point to this, is that obviously Kelvin basically recognized the significance of this, and basically what that means in terms of our gas law is pretty much every single gas law that you come across, the temperature does need to be in Kelvin. So it definitely needs to be in Kelvin. That means the two that we just saw, which was Charles' law at constant pressure, those guys there need to be in Kelvin. And also Guy Lussig's law there, P1 T1 equals P2 T2 at constant volume, also needs to be in Kelvin. And like I mentioned a second ago, pretty much if you're dealing with a gas law and you're dealing with temperature and you want to be safe, it definitely for sure needs to be in Kelvin. So you always got to make sure temperature is in Kelvin when you're dealing with gas laws. Any questions on that there? All right, so let's take a look at one here. And again, as we've talked about before, when you're converting to Kelvin, you can't leave the 0.15 off. It's okay. So see what you come up with here. We are looking for what temperature will we have a volume of 1.54 liters. Okay, so let's take our same approach we've been doing. We're going to pull out the information. So we have a volume that is 3.2 liters. We obviously have a temperature that is 125 degrees Celsius. We're looking for another temperature here, and we are having a volume of 1.54 liters. So we got a couple of volumes, a couple of temperatures that again should kind of visually point you to Charles' law here, which is V1 T1 is equal to V2 over T2. This obviously is that constant pressure. In this particular case, again, we can label these guys as ones, these guys as twos. We do need to do a couple things. Let's see, volume here, they're both liters, so that's okay. We do need to add a 273 here to our Celsius because we do need to get it into Kelvin. And that looks like we then would be at a 398 Kelvin. In this case, we're solving for T2. So basically remembering that, as we talked about, you could kind of do the crossover move, right? So again, if we're kind of going that way or that way, that way or that way, we do want to get T2 really on top and by itself, which means we need to take T2 to the other side. So we got to kind of bring this guy this way. In addition, we need to bring the other guys the other way as well. So we need to bring this guy, whoops. We need to bring that guy that way and this guy back there to that spot there. So if we do all that rearranging there, we end up with properly rearranged, hopefully, as T2 is equal to V2 times T1 and V1. Again, bringing V1 down, bringing T1 to the top, and T2 to the other side. Again, you want to make sure that you can rearrange this properly. You're basically multiplying by T2 to both sides, multiplying T1 to both sides, and dividing by V1 to the other side. So if we put all of our numbers in, we want to make sure we get our correct numbers in the right location. So we're looking at V2 up on top. We're looking at T1 on the top there and V1 on the bottom. Again, the liters will cancel. That's going to leave us Kelvin left over, which is good because we are looking for a temperature. And we get 1.54 times 398 divided by 3.2 gets us about a 192 Kelvin. And again, here, if we sort of look at our relationship, what we see is our volume has decreased, which means based on our relationship, we should see the temperature decrease, went from 398 to 192, or minus 81.5 degrees Celsius. Also went down as well. So we do see the correct relationship there. Any questions on that calculation? Okay, we will stop here for now.